Okay, threads. So we'll talk briefly about threads today, but there is a whole chapter on threads, which is chapter 4. So what we need to know here is that many systems, in fact, I think all general purpose operating systems today support threads. And what a thread is a sub-process or a lightweight process. A thread is a lightweight process. So a process may be divided into threads, and that's usually something that the application designer, it's a design decision to design an application such that it's multi-threaded. Now when an application is multi-threaded, the operating system needs to track the behavior of each thread separate. So most of the information in the process control block, probably all the information except the process ID, must be kept on a per thread basis. So each thread will have its own program counter because it's a separate thread of execution. It will have its own program counter, it will have its own CPU registers, it will have its own accounting information. So most of the information in the process control block will be thread specific or is tracked on a per thread basis. Okay, more details about threads will be discussed in chapter 4. Process scheduling. We already now know about process scheduling, and we now know very well what the scheduler is. We still don't know what algorithms operating systems use for scheduling. We still haven't discussed the algorithms, but we know what the scheduler does. So it's the scheduler is that part of the operating system that selects the next process for each CPU. Now we have the important concept of a queue, or the different queues in the system. In an operating system, there are many queues. One of them is just the job queue or the list of all processes in the system. This is where all processes will reside. And there is the ready queue. In the ready queue, the system will maintain the processes that are ready to take the CPU. And each device will have its own queue. Each I/O device will have its own queue. In that queue, it will keep the processes that are waiting for that particular device. In fact, it's not only devices have queues, but as we will see later, events may have queues as well. Events like messages or semaphores will have their own queues. So in an operating system, there are lots of queues, and the process will be moving from one queue to another. And to illustrate this, we will look at this example. So in this example, we have a ready queue. There will always be a ready queue. There is that queue for the CPU, the processes that are ready to take the CPU. And in this case, we have 4 other queues, a couple of magnetic tape queues. Here, we are emphasizing the point that each device has its own queue. And we have a queue for disk 0 and a queue for terminal 0. Just examples. Now, at this point, processes 7 and 2 are ready, so they are in the ready queue. While this device doesn't have any processes in its queue. And this applies to this device as well. This device has 3 processes that are waiting for it, that are in the waiting queue for that device. And this device has 1 process in its waiting queue. Now, process number 3 is the first in the queue. At some point it will get serviced by the device, so the device will service process 3, and when this device completes servicing process 3, it's going to notify the kernel by generating an interrupt, And when that interrupt gets generated, the kernel takes control. And one of the things that the kernel will do at that point is putting P3 in which queue?
Ready queue? The ready queue?
The ready queue, yeah. After the completion, so when P3 is done with this device, and the device notifies the kernel via an interrupt, the kernel is going to put P3 into the ready queue. It's not going to give it the CPU immediately, right? It never gives the CPU immediately. But it may get there. It will put it in the ready queue, and it may or may not get the CPU depending on which other processes are in the ready queue. There may not be any. And it depends on the scheduling algorithm. Okay, another diagram. So this diagram, by going through this, we will just be emphasizing the concepts. It doesn't have any new concept, in fact, but we will just be emphasizing the same concepts. So a process starts off in the ready queue, then at some point it will get dispatched by the scheduler, it will get the CPU, and when a process is on the CPU, many different things can happen. Here we will look into 4 different things that may happen. One is requesting I/O. When it requests I/O, it will be in the queue for that I/O device. Then when that completes, the system is going to put the process in the ready queue. If the process gets interrupted by the system, the timed interrupt that the kernel set up, the process will be placed in the ready queue. If a process creates another process by forking a child, for example, so that child that gets created will not just get the CPU, right? So think about it. You have a single CPU system. You have only one CPU. And the process creates another process. So it will be impossible for both to be on the CPU because the CPU can have only one process at a time. So when a process creates another process, the process that gets created will be put on the ready queue, in the ready queue. And then the child and the parent will be competing for the CPU, if there is a single CPU. If there are multiple CPUs, the system may put each process on a different CPU. And they will be executing in parallel. Later on, we will be making the distinction between 2 processes executing in parallel and 2 processes executing concurrently. It's an important concept that we will be explaining in chapter 4. Now, if a process is waiting for something, waiting for an event, like a semaphore or a message or whatever, then it will be waiting until that event occurs, and it will be an interrupt will trigger that, and the process will be placed in the ready queue. Okay. So now we will talk about more about scheduling. So in operating systems, an operating system may have different kinds of schedulers or different levels of scheduling. Well, the main scheduler that we focus on and is always there in all operating systems is the short-term scheduler or the CPU scheduler. This is what we would like to focus on, the short-term scheduler or the CPU scheduler. It's that scheduler that looks at the ready queue, and the ready queue is in memory. Keep in mind that the ready queue is in memory. The ready queue is a kernel data structure that is in memory. Whether it's in the cache or not, we don't know. But it's in main memory. Now this short-term scheduler looks at the ready queue and according to a certain algorithm picks a process for each CPU. Now, some systems may have a long-term scheduler that will decide or that will select a subset of processes to be in the ready queue. So why would the system put only a subset of the processes in the ready queue? Maybe for memory limitations. If memory is limited, then the system may not be able to put all processes, to keep all processes in the ready queue. So long-term scheduler that many systems do not have. So not all systems have a long-term scheduler. It selects which processes should go into the ready queue. But remember, our focus is on this, is on the short-term scheduler or the CPU scheduler. Now, processes can be described either as I/O bound or CPU bound. So this is an important concept that we need to understand. Well, the brief description is a CPU-bound process is a process that does a lot of CPU or that spends most of its time doing CPU, while an I/O process, an I/O-bound process is a process that does more I/O than CPU. So if a process does more I/O than CPU, it's I/O bound. If it does more CPU than I/O, then it's I/O bound. Okay, if it does more CPU than I/O, then it's CPU bound. If it does more I/O than CPU, then it's I/O bound. So this is well, let's do two different processes, and then I will ask you which one is CPU bound and which one is I/O bound. If a process has these characteristics, it has, this is what we call CPU burst. This is the typical behavior of a process. It has a CPU burst. Then it requests I/O. Then after the I/O, it has another CPU burst. And another process may have the following behavior. CPU, then I/O, and CPU, I/O. Well, when we say I/O, here we are describing the behavior of a process. But how long will that I/O take? That's not under the process's control. It depends on the system. It depends on the availability of that I/O device and on the speed of that device, how fast or slow that device is, and how many other processes are competing for that device. Because if more processes are interested in that device, then this I/O time will be longer, right? Because the process will be spending more time in the queue for that I/O device. Okay. Now this is process 1, this is process 2. So is process 1 CPU bound or I/O bound? Yeah, CPU bound because it does more CPU. Process number 2 is I/O bound because it does a lot of I/O. Now, what kind of process or what kind of program do you think will be doing this? When you look at this, what does this tell you about the behavior or the nature of that program? How would you describe the behavior of a program that does this?
Keeps constantly looking for user input.
Yeah, which means that it's likely to be an interactive. It's an interactive program. A program that interacts a lot with the user. It will be doing lots of I/O and spending a small amount of time processing user requests and then requesting more input from the user. Okay, so this is an interactive program. What kind of program is this?
Calculation.
Yeah, lots of calculations, exactly. So it's a program that does lots of calculations, like a scientific program, right? Or an image processing program. It does a lot of computation. Well, if it's on the GPU is another story. But well, let's focus on the CPU at this point. So, if a scientific program will have characteristics like this. So this is CPU. This is CPU bound. This is I/O bound. Now, why do we need to know this in the context of operating systems? In fact, when we get to scheduling, we will see how the scheduler will be treating these two kinds of programs differently. But what we need to understand at this point is that for good performance, for good system performance, we should have a mix of I/O bound and CPU bound processing. Why is that? Why do we have to have a good mix of CPU bound and I/O bound? Or in other words, another way of asking this question is, what will happen if all the processes in the system were CPU bound?
Your queues are going to get very backed up.
Which queues?
Well, it depends on, it depends on what kind of processes you have. So
With this.
So that one, your ready queue will probably be really full, because you've got a lot of processes that are waiting to get on the CPU, but one's taking up a ton of time.
Yeah, exactly. So with this kind of processes, if all the processes in the system were like this, then our ready queue will be full. There will be lots of processes that are waiting for the CPU because they all want to do the CPU. And what will the I/O device queues look like? They will be empty. Nobody, because the processes, the critical resource in this case that the processes are competing for and want most of the time is the CPU. So the processes will be spending most of their time waiting for that resource that is in high demand, which is in this case the CPU. So big ready queue, empty device queues. Now with this, it will be the opposite, right? So processes will be spending most of their time in the I/O device queues, and the ready queue in this case will be empty for long periods of time. For long periods of time, the ready queue will be empty. Why? Because all processes are not ready. They're waiting on some I/O device. Okay? Now, in terms of resource utilization, if all processes are like this, we will not utilize resources properly because they will all be waiting for the CPU, and we will, the CPU will be overutilized, but all other resources will be underutilized. Here, the processes will be spending lots of time, waiting for I/O. But if we have a mix of the two, mix of CPU and I/O, all resources will be utilized, and the scheduler will always find some process in the ready queue to give the CPU to, and the devices, while other processes are getting serviced by I/O. So while some processes are getting serviced by I/O, another process or other processes, depending on how many CPUs you have, will be running on the CPU or the CPU. Okay? So it's an important concept. Do you think, by the way, and one important question, do you think that the operating system will be able to classify a process as CPU bound or I/O bound? Does the operating system know this?
Probably not.
Does it know this? Or if I ask you to write an operating system kernel, and can you write some code, some operating system code that will classify a process as I/O bound or CPU bound? Can you?
What it is.
No, I don't need to know what it is. I don't need to comprehend. See, an operating system does not comprehend processes. It doesn't know. It doesn't know what a process is doing. It doesn't have the notion of understanding the semantics of a process. An operating system doesn't know, but it knows the behavior. And what behavior is just what we have on the board. The behavior is how frequently does a process request I/O, how much CPU time does that process demand, and this is something that the system can track. You can track it. You can track the history of the process, the behavior of the process. You know, how often it requests I/O, what was the length of the last n CPU bursts of a process, you know, how much the last n times the process was given the CPU. Did it use its entire time quantum, or it requested I/O before its time quantum expired? Yeah.
So how can it do that if it's never seen that process before? Because what you just stated.
Well, we're saying it keeps track of the history. Yeah, so the very first time, the system doesn't know anything about the process.
So it
When a process is starts running, it has no history, and the system has no idea about its behavior. But as the process runs, the system will be tracking the behavior of that process, so it will be saving information about that process, and then it will know about its behavior, and it will treat it. It will treat it accordingly, you know, based on its behavior.